Alright, so in this video I'm gonna be explaining about another domain adaptation paper, which is called unsupervised adversarial domain adaptation for implicit discourse relation classification. So this paper in 2019. First, I need to show you some background on generative adversarial networks, although I have a playlist for generative AI that I have explained GAN, conditional GAN, and many other generative AI models. So we have a discriminator. We want to design this generator so that it fools this discriminator, because discriminator wants to say that if your image is real or synthetically generated. But if you change and learn these parameters correctly, of course for backpropagation, then you can fool the discriminator. So this min-max game is the result because you have loss generator and discriminator loss and generator loss. And this is the idea of GAN. So implicit discourse relations are not only more challenging to classify, but also to annotate than their explicit counterparts. We tackle situations where training data for implicit relations are lacking and exploit domain adaptation from explicit relations. Because some relations have very rare training data for them, and so we exploit domain adaptation from explicit relations. We present an unsupervised adversarial. For example, if you have many training data, then you have rich data, many data, but you have a scarcity in your target. So that is a good way to define target and the source domains. But unsupervised domain adaptation is very challenging in comparison to semi-supervised or anything else. Of course, we don't talk about supervised domain adaptation because it's just fine-tuning and everybody knows that. And of course, you don't always have labels. They are expensive. So this is a very good article, a survey of implicit discourse relation. And you have implicit discourse relations. For example, one sentence is contingency for another sentence or argument, let's say. The submission deadline is coming. And we have this connective because. So this is just an example of implicit discourse relation, what we mean by that. You see, it has a structure. It's not just simple label prediction, it's a structured prediction. Structured prediction is much harder than just ordinary simple label prediction. And there are many problems that can be formulated as structured prediction, such as semantic parsing, dependency parsing, discourse parsing, let's say event extraction. There are many. That's why it's very natural. But it is still unknown in neuroscience how our brain can handle these complex problems. So we use ADDA, and I have explained it I will explain it in part 20 of the current playlist for domain adaptation. So because it first learns a discriminative representation for classification task in the source domain, then learns a representation for a target domain that mimics the distribution of the source domain. The key insight here is asymmetric mapping, where the target representation is updated until it matches with a source, a process more similar to the GAN idea. So this figure shows the summary. We first pre-train a source encoder and source classifier, then train the target encoder and discriminator in an adversarial way to minimize domain discrepancy between the target representation distribution and that of the source. Eventually, the target feature space is trained to match the source, and the source classifier can be directly used on the target domain. So this is the framework of our proposed adversarial domain adaptation. First, you do pre-training because you have your source, so simply just find the class labels, predict them. Then you go to another stage, you have adversarial adaptation. Because you not only have your source domain, but also you have target domain. So it shows if it is, you should fool the discriminator. This discriminator should be fooled by appropriate design of these encoders. Then we get a reconstruction and we have fixed feature. And for testing, you just use the target encoder that we have designed here. So the source and the target encoders follow the same architecture. M sub t is initialized to be M sub s during adaptation. The encoders encode relation arguments into latent representations and then feeds their representations into a classifier to predict the discourse relation. This is a neural architecture of the BiLSTM to encode relation argument pair. Because we can formulate this problem of discourse parsing into just a relation argument pair, because we have a pair of relation arguments, and then we can gradually build this hierarchical structure. So specifically, we encode each word in an argument into its word embeddings, which are fed into BiLSTM to get hidden representation Z sub I using a fully connected layer on top of the concatenated hidden states. We then apply an attention mechanism to induce a distribution of weights over all tokens in the argument. The final argument representation is a weighted sum of Z sub I, based on this attention weights alpha sub I. Because it's attention weights, so it's just a linear combination of your Z sub I. Because Z sub I is your, as I said, this hidden representation of your LSTM. Then we have classifier. So until now, you know labeled data of source domain, so you can classify. Then we move on to the adversarial part, and then you get this idea of GAN to just reduce domain shift, and so you don't have a covariate shift problem. Spectral normalization. So to stabilize the training of discriminator, we employ spectral normalization, a weight normalization technique, which controls the Lipschitz constant of the discriminator function by constraining the spectral norm of each layer. Spectral normalization is easy to implement without tuning any hyperparameters and has a small additional computational cost. And also label smoothing. We utilize label smoothing to regularize the classifier during pre-training, which prevents the largest logit from becoming much larger than all others. So we smooth it, because otherwise it produces overfitting. For a source domain training example with ground truth Y sub S and ground truth distribution Q, the classifier computes the classification probability over relation classes. And then we have reconstruction loss. In order to classify the target representation using source classifier, the target encoder is trained to produce representation that mimic the source domain representation in an adversarial training stage. Since there is no supervised loss applied in this stage, the target encoder may lose its ability to produce discriminative features that are helpful during classification. We propose a reconstruction loss to preserve the discriminability of the target encoder when adversarial adapting its features. Since we initialize the target encoder with the source encoder, the initial representation of a target instance is the representation of target instances produced by the source encoder. After training, M sub t adapts to the source domain and becomes dissimilar to M source of xt. The reconstruction loss encourages a target encoder to produce features that can be reconstructed back to ms. So for target example x sub t, we learn a reconstructor mapping. This is your reconstruction mapping that maps the target representation to m sub s. The target encoder and the reconstruction mapping are jointly minimized. So we have a source and then reconstruction of your target of x sub t. Then it should be minimized. I think the intuition is that if they have a good loss, then it could enhance training, and the natural loss that you can create is just a trick of reconstruction, because we know if we create a map, then we can have a good loss for backpropagation. Because we always augment all these losses, reconstruction is one of them. So it can avoid overfitting in this way. So we train this classifier for source, then adversarial, and then reconstruction.